Let's now state and prove the unique factorization for theorem for complex polynomials, or for polynomials with complex coefficients. The statement of the theorem is that, and I'll leave it up here, let f of x be a polynomial with complex coefficients with degree n. Then there is a unique constant a and a unique collection of complex numbers, the roots, c1 through c sub n, not necessarily distinct, so that f of x is equal to the leading constant a times x minus c1, x minus c2, through x minus cn. So every polynomial has a linear, can be completely factored into linear terms as long as complex numbers are used. And furthermore, that factorization is unique up to just shuffling the terms. So for example, if this, I could have a 1 here and then a 2 here, or I could put a 2 then a 1. Except for the order of the terms, the factorization is unique. Okay, now the proof of this is actually by induction. So to start the proof, let's take a look at the case n equals 1. If n equals 1, that means that I have a polynomial of degree 1, which has the form ax plus b. And this clearly has the form prescribed. I can factor out the leading term a, and that gives me a times x plus b over a. A is not equal to 0 because I have the polynomial degree 1, so the a cannot be equal to 0, so the division here is permissible. And that clearly has the form required, where I let c1 be equal to negative b divided by a. So x minus negative b over a is the same thing as x plus b over a. So this clearly has the form. I have a unique constant a and a unique root c sub 1. For the next step, we proceed with the induction hypothesis. In our case, the induction hypothesis would be that every polynomial of degree n has the factorization prescribed. That if I have a polynomial of degree n, then there are unique numbers c1 through c sub n and also a unique leading coefficient. We now proceed to the inductive step. Suppose n plus 1. So let f of x be a polynomial, now with degree n plus 1 as opposed to degree n. We need to work our way down to a polynomial of degree n so that we can use the induction hypothesis. To do this, we'll use the fundamental theorem of algebra. The fundamental theorem of algebra dictates that there must be some complex number c, and I'll call it c sub n plus 1 for reasons that'll become clear, so that f of c sub n plus 1 must be equal to 0. If I have a complex number, so that if I plug in the complex number I get 0, then according to the factor theorem I can factor the polynomial. Now that's true because I have a polynomial as opposed to some other kind of function like sine or log, but because f is a polynomial, then I can factor f as x minus this root c sub n plus 1 times some quotient to be determined. But whatever that quotient is, it must have degree n. F of x has degree n plus 1, x minus something, that's a degree 1 polynomial, and so the q polynomial has to have a leading term of x to the n, so that f of x has a leading term of x to the n plus 1. So x minus c sub n plus 1, that's degree 1. Q must be degree n, so that f of x has an x to the n plus 1 term for degree n plus 1. So here I have a degree n polynomial. Well, if I have a degree n polynomial, by the induction hypothesis, every polynomial of degree n has the factorization that's prescribed. And so writing that out, I have that f of x can be written as a times x minus c1 times x minus c sub n. So the part that is underlined in red here, this is the q sub x term right here. And then the other term, x minus c sub n plus 1, just simply comes along for the ride and is multiplied by q of x. So the q of x term has the required factorization. The extra term comes along for the ride, and so I have a factorization, unique factorization, with a constant up front, a, and n plus 1 complex numbers, c sub 1 through c sub n, and then the extra term, c sub n plus 1. And so that is the end of the proof. of the unique factorization theorem. I should mention parenthetically that the textbook mentioned that this is sometimes called the fundamental theorem of algebra. Most pre-calculus books that I've seen call this the unique factorization theorem, and they call the fundamental theorem of algebra the theorem that states that a polynomial has one root, which is the way that it's stated here, that by the fundamental theorem of algebra, a polynomial must have at least one complex root. But the textbook did mention that some textbooks like to call what you see on the screen now the fundamental theorem of algebra, and it is indeed logically equivalent to the one that we're using in this class.